Antimatter, the counterpart to the matter that makes up everything we know, holds profound potential as a fuel source, particularly in the realm of space travel. While the concept often features in science fiction, the real-world science and technological implications of using antimatter as a fuel are immensely challenging and equally fascinating. Antimatter particles are identical to their matter counterparts except for opposite charges. When matter and antimatter meet, they annihilate each other, releasing energy according to Einstein's famous equation, E equals mc², which indicates that even a small amount of antimatter can release a tremendous amount of energy. The incredible energy density of antimatter makes it a highly attractive potential fuel. 1 gram of antimatter reacting with 1 gram of matter would release energy equivalent to about 43 kilotons of TNT, or roughly 3 times the energy released by the atomic bomb dropped on Hiroshima. This immense energy potential suggests that even a minuscule amount of antimatter could be sufficient to power spacecraft far more efficiently than conventional chemical rockets or even nuclear propulsion technologies currently under consideration. However, the production of antimatter presents significant scientific and engineering challenges. Antimatter is naturally occurring but exceedingly rare in our universe, appearing in minute quantities as cosmic rays or produced in very small amounts in high-energy environments such as those around black holes or during certain types of radioactive decay. The most practical method for obtaining antimatter is through particle accelerators, where high-energy collisions create pairs of matter and antimatter particles. The problem is that these processes are incredibly inefficient and expensive. Currently, producing just 1 milligram of antimatter would cost billions of dollars and require more energy than it would eventually yield as fuel. Beyond the hurdles of production, the storage of antimatter poses another significant challenge. Antimatter must be stored in a perfect vacuum and suspended away from any matter to prevent annihilation. This is typically achieved through the use of penning traps or magnetic fields which can contain charged particles such as positrons or antiprotons. These storage methods are effective but complex and have not yet been scaled to the levels necessary for fuel applications. The slightest failure in containment would result in the immediate annihilation of the antimatter with the surrounding matter, leading to potential loss of the spacecraft and mission. Another aspect to consider is the controlled release of energy from antimatter. In theoretical spacecraft designs, antimatter could be used to initiate small, controlled reactions that propel the spacecraft. This could be achieved through the use of antimatter-initiated microfission/fusion, where small amounts of antimatter induce fission or fusion reactions in traditional nuclear fuel materials, thus amplifying the energy output without requiring large quantities of antimatter. Such technology would leverage the high energy release from antimatter but remains theoretical at this stage. Theoretical applications of antimatter extend beyond propulsion. In theoretical power generation systems, antimatter could be used to heat a working fluid or drive turbines, much like nuclear power plants, but with a much higher efficiency and energy output. These applications could revolutionize not only space travel but also power generation in remote or high-demand scenarios on Earth. Despite these possibilities, the current technology and understanding of antimatter limit its practical application as a fuel source. The focus of contemporary research is on improving the efficiency of antimatter production, developing better containment methods, and exploring potential applications in high-energy physics experiments. As technology advances, however, the potential of antimatter to play a crucial role in future energy systems and space exploration remains a tantalizing prospect. In conclusion, the use of antimatter as a fuel source, while promising, is currently relegated to the realms of theoretical physics and advanced engineering research. The barriers to its practical use are substantial, involving not only immense costs and technological hurdles but also fundamental questions about feasibility and safety. Nevertheless, the pursuit of antimatter as a potential fuel continues to inspire both scientific inquiry and imagination, holding a place as one of the most intriguing frontiers in the intersection of physics, engineering, and space exploration.